once again, it's the physics video lecture. This is psci 168, video lecture number 2. And I want to start by talking about our lecture notes, which are going to be your book in the course of the semester. So let's see what we have here. We're trying to take really good handwritten notes, and of course you're going to turn in Monday, Wednesday, Friday notes to me every Friday. So they're handwritten, and you take a picture of them. We eventually want to compile them into a book. So along the way, I will send out little handouts to you. For example, today I'm going to send one out. And also you guys will be taking screenshots and images and stuff and printing them out. So for example, last time I asked you to print out a Greek alphabet, right? You print out the Greek alphabet, and that's one of the pages of your notebook. So I'm just going to write here, print out images. So just don't send me the image, but actually send me a picture that you took of the printed out image, because it's going to go in your book. So images and screenshots and other stuff as well. So that all goes into your book, and it all goes into your lecture notes that you take a picture of and send me once a week. So handwritten, print out images, and also homework problems. Also, just in the course of your lecture notes, you may solve them on a separate piece of paper and file them in as well. The way you organize that is up to you. These homework problems will be the type of thing that ends up on the exam, so it'll be practice for them. And you can always send me an email if you want to have something demonstrated up on the whiteboard here, next week. So eventually, all of these things will be put together into a book. And at the end of the semester, you'll number the pages, and you'll produce a table of contents and an index and maybe even a glossary, and it should look really good. Last semester I had some really good examples of that. And so I'm pretty optimistic. This should work out nicely. For the moment though, you're taking these handwritten notes, practicing everything I do, printing out stuff, either that I send you or that I ask you to look up online, and just to get some images of everything we're talking about, and the homework notes as well. So eventually, we're going to have numbered pages. At the very end of the semester, table of contents and an index. So that should be enough for getting started here. So where we were last time is we realized that we needed some arithmetic and geometry in order to do things more precisely. I had motivated it out of tracking game, reading shadows that trees cast, things like that. And we had taken the idea of a vertical stick casting a shadow on the ground and realizing we could actually use that system to figure out how many days there are in the year. So yeah, we need arithmetic and we need geometry. So I'm going to start out with arithmetic. And the technique that we need is to be able to use scientific notation and powers of 10. So the scientific notation, and this is actually kind of fun. Scientific notation, we want to express just some large number. I'll make up a big one. 4, 3, 2, 1, 2, 3, 4. Okay, that's some big number. And I'm going to not write equal, but approximate. It's an approximation sign, because we're just going to do what's called take a couple significant figures. That's 4.32 times 10 to some power. And we can read it off here. There's our decimal, so 1, 2, 3, 4, 5, 6. Okay. times 10 to the 6th, right? We could have also set commas like that. Okay, 4.32 times 10 to the 6th, 4.32 million. Okay. And I can do another one, 0.0054321. Okay, that's also some small number this time. And again, we're just going to take a couple of significant figures. So we have, let's write that. We have 5.4. I'm just going to go ahead and approximate it to 5.4 times 10 to the minus 1, 2, 3. Okay, to the minus 3. And so large numbers and very small numbers, they don't faze us in the least, because we can express them just in terms of scientific notation here. Now suppose I give these a name, A and B, and I want to multiply those two numbers. Okay. If I gave you these two numbers to multiply, you wouldn't be happy. Well, let's look at this again in terms of approximations. So multiplication, we're just going to multiply A times B. A, B, I'm going to go straight to the approximation. It's 4.32 times 10 to the 6th times 5.4 times 10 to the minus 3. And what's the technique? It's just to multiply these two numbers together and then deal with the exponents. So again, approximating 4.32 times 5.4. Well, 4 times 5 is 20, so this is some number that's a bit bigger than 20. So I could just approximate it with 20. Can we do a little better than that? 4 times 5.4, 20, 4 times 0.4 is 16. So I'm just going to go 22. Approximately 22 times 10 to the 6 minus 3. If you've seen this before, good. If not, I'll get into it a little bit more. But we're not quite there yet. Now this one we're going to say 2.2 times 10 to the first power, that's our 22, plus 6 minus 3 equals 2.2 times 10 to the fourth power. If I didn't make any mistake here. Okay. But I think that's roughly what we have going on here. So yeah, you can just add the exponents when you're multiplying something like this. Next one we're going to do is a division. But so now we put it back in the scientific notation. And what you'll find interesting, because of course you guys can do this too, is to play around with a number like this. Pair of numbers is make them up. Go ahead and do this, and then take out your calculator and do the actual multiplication. You're going to find that you're within 5 or 10%, no problem. Okay, and so we completely lose our fear of numbers, and we realize that we don't need all that accuracy that's spurious. Right? We need to get a good idea of what these, relations are. So yeah, go ahead and practice one of these. The next thing I'm going to do is the division. So if you want, leave some room in your notes, leave some space, and make up a couple more. So now let's divide these two numbers. And see what happens. Okay. So how about we do B divided by A? Again, if I just ask you to do that, you'd look at these, might throw up your hands, but we're going to make it simple. So B divided by A, we have a 5.4 times times 10 to the minus 3 divided by our 4.32 times 10 to the 6. Okay. So this is going to be, we're going to have 5.4, actually this is still equal, divided by 4.32 times 10 to the what? Minus 3. And because this is in the denominator, 10 to the minus 6. Okay, so, I'm sorry, yeah, 10 to the minus 3 minus 6. And now this 5.4 over 4.32, what is that? Slightly greater than 1. I'm just going to say approximately 1.1. You can look it up in the calculator. And then what do we have here? 10 to the minus 9. 10 to the minus 9. So a very small number. Okay. And that's how easy it is and how fast it goes. So we definitely need scientific notation. Here's a globe here. This is a meter, okay? How many meters in our actual Earth? We're gonna learn about that, in a couple of hours from now. And it's 6 million meters in radius, roughly. 6 million meter radius, and that would be 6 times 10 to the 6th power. And on the other hand, if you go into the smaller regime, a meter stick has 1,000 millimeters. Right, the metric system's great because of the decimal system. But yeah, meter stick has 1,000 millimeters, a really small increment there. An atom or a molecule could be 10 to the minus 9 meters. So it could be a millionth of a millimeter, right? Too small to barely even imagine, and yet we can just deal with these kinds of numbers very easily using scientific notation. So we'll have everything from the microscopic, the atomic sizes, all the way up to the Earth, the solar system, and the cosmos, and we can just deal with those types of relations by working with scientific notation. In fact, it's the only way. You'll see numbers like this written out in order to impress you in some book or magazine article, but these types of numbers don't impress us. They mean very little to us. Okay, we can't really grasp them. With scientific notation, you immediately know, the basic number and the power of 10 that goes with it. Good, so we did multiplication and division. We just write the exponents generally. We have 10 to the A times 10 to the B. If these are, 10 to the A power, 10 to the Bth power, that would just be 10 to the A plus B. Okay. If we had 10 to the A divided by 10 to the B, that would be 10 to the A minus B. Okay, so if it's an exponent in the denominator, that's the negative exponent in the numerator. So those are the two rules I just made use of. And again, you can make some of these up yourself, try this out, take out your calculator and see how accurate your original estimate was. And I think you'll be pleasantly surprised. Good, so that's the major aspect of arithmetic that I wanted us to know about and practice. Now there's a really good video that I'm going to put in our playlist, and let me mention that next. It's a short, I forget, maybe about 10 minutes long video, or maybe less, called Powers of 10. And I'll just say a couple of words about that. I'll put it in the playlist, and I'll tell you what we want to do there. So video, we'll call it demonstration here. I've played this in class before, but I'm just going to send you guys out to watch it. So it's called Powers of 10. It'll be in the playlist by Charles and Ray Eames. This is from the 1970s. This is a famous married couple, who did all kinds of interesting stuff in design and other creative stuff. But this video kind of embarks on a cosmic journey, just starting from out in a football field all the way to the edge of the universe and then back again. And it's a very nice example of the use of powers of 10 in just terms of the size of the universe, all the way from the cosmos on down to little atoms and molecules. So you want to watch this. So watch the video. This is homework. Watch the video and then print out a couple of good screenshots. So if you print out some screenshots, and if you're ambitious, you can kind of format them to look good in your book. So, but I'll just say print out some screenshots. That's the first thing. The second thing is I will email you the text to this. So it's a very interesting text narration done by a guy named Philip Morrison. This is way back in the 1970s. Famous physicist in his own right. There's so much information in this video, you can't take it all in just seeing it once anyway. So I'm going to have you print out the text or the transcript of the narration. Okay, I will email that to you because it's harder to locate online anymore. I found one, I didn't find the one I used to find, which was a little cleaner. So I found one and put it on a Word document and say, I will email. So that'll show up in your email. Go ahead and print that out as well, because we want both of these in your book. And not only print it out, but reread it a couple times. You'll see it's pretty interesting. Good, so that is our discussion of arithmetic. And we lose our fear of big numbers, small numbers, if we just know these techniques right here, powers of 10. Good, next is geometry. We saw we needed geometry just if we were going to build an accurate sundial. In fact, you want to build anything accurately, you need some knowledge of geometry. So for that reason, we'll derive some famous geometrical formulas, useful ones. And let me say something about this. All of these exercises that I do, of course you want to put them in your lecture notes. Be a good idea if you practice them as well. I'll be drawing circles, triangles, I'll be labeling them. I just did a little arithmetic on the board. And if you're not a science major, you may not have been practicing these things as much, but practice is what makes it easy. There will be lots of formulas during the semester, and the whole idea here is if you go through all of these practice moves of algebraic, geometric exercises, you'll just get a lot better at it. Okay? So if you practice these things, if you draw circles and triangles 1,000 times, you get pretty good at it. So in that spirit, I'd like you to just take everything down that I do and practice it, which means just to repeat it and think about it. Leave some space in your notes, do a little more, or use a piece of scratch paper. And then in the course of the semester, everything we do will become easier and easier. Okay. Good. So what about geometry? What do we need to know in geometry? We're going to need lengths, areas, and volumes. And if we have a unit of length, we will use the meter. Okay, the general unit of length is the meter. Metric system just uses powers of 10 of the meter, so that's very easy. So actually, before we do the geometry proper, let's just talk about our unit of length a bit. Unit of length, it's the meter. It's abbreviated just with the letter M. You know, if you want to know about what the meter is with respect to the size of your body, well, then you can do this kind of thing, and it's actually basically a body-sized unit of length. Now, in terms of the scientific notation, we have the centimeter, abbreviated cm. That's 1/100th of a meter. So we can also say that's 10 to the negative 2 meters. We have the millimeter, and that's the smallest increment on one of these, typically on one of these rulers. The millimeter is 1/1000th of a meter, or 10 to the minus 3 meters. If you go in the other direction, 1,000 of these is a kilometer or kilometer. So km equals 10 to the positive 3 meters, right? So our decimal system's really nice in terms of that. That's about 6/10 of a mile. Conversions we'll deal with later. Okay, so there's our unit of length, but otherwise we can always just write down some letter for a unit of length, A, B, C, D, and so forth. So yeah, let's talk about that a bit. Our metric system. Length, I'll just use the letter L. And I've marked off some length. Area, L squared. I would have L times L, that would be an area, and a volume, L cubed, and then I would draw a cube here with all three sides length L. It would be a volume L cubed. If we're using the metric system, we could have a meter, a square meter, and a cubic meter. Okay. So we're using those kinds of expressions. Now suppose we let's start with a triangle. We're going to do a little bit of work with triangles. So let's go ahead and draw one. There's a triangle. And what can we do? We can label the angles in here. We can talk about the area of a triangle. Since we're talking about areas here, how about we talk about the area in this triangle? And what I'll do is draw a parallel line to the bottom here and first construct a rectangle. And for my rectangle, I have base and height. So the area of the rectangle is B times H. I think everyone will agree. Now I see a symmetry here. And so the area bounded by this triangle is apparently 1/2 the area of the rectangle, because these two are equal and these two are equal. So area equals 1/2 base times height. That's an important formula for triangles, and I'll just kind of indicate what I said here. Area of the rectangle, I'll just write here, area rectangle was B times H, and therefore 1/2 base times height. Yeah, that's something we'll make use of. What about angles? Had everybody download the Greek alphabet, because we're going to start talking about angles, and we often label those with Greek letters. So now we've got our Greek alphabet available. So again, we have a triangle, and how about pretty much the same one there? And this time I'm going to label these angles alpha, beta, gamma. Okay. So how about the sum of those angles? Well, the first thing we're going to do is draw, kind of like we did up there, the parallel line to the bottom line. Okay, that's parallel. And now we're going to extend all of these black lines of the triangle. So we'll extend this, and I'm going to extend this one here as well. So we've got these two parallel lines, the blue line and the black line, and we're extending all of these. So now what have we won? We see by symmetry that this angle alpha is the same as that one right there. This angle beta is found right here. This angle gamma is found right here. You know, once the picture's done, you're going to want to reproduce the construction. So where else do we find alpha, beta, and gamma? Okay. Here, I'll do this in red just to indicate what's going on. So right here we have an angle that we find up here again. Okay. And I'll go around with those. But yeah, we see that we have alpha here, and the same argument for gamma tells us that we're going to find it there. Okay. So suddenly we have this alpha, beta, and gamma, and we find that alpha plus beta plus gamma is equal to two right triangles, which we can also call 180 degrees. Okay. So right here, we found alpha plus beta plus gamma equals 180 degrees. And of course, the number of degrees is just a convention. So strictly speaking, we could say it's equal to two right triangles, but each right angle equals 90 degrees. Okay, so two right angles, 180 degrees. But again, very useful that the sum of these angles equals 180 degrees. Okay. Good, so we have that. Now I'm talking about right angles, so of course the next thing we want to talk about is a right triangle. That's a triangle, and then we have the right triangle. And the right triangle, which I'll draw right under here, has a right angle. And we'll go ahead and label A, B, and C. There's some tradition there. Okay. We could also be interested in the opening angle here if we're doing trigonometry. But we've got that right triangle, and everybody's already thinking of the Pythagorean theorem. Okay. What we can say is, since that's 90 degrees, we can say that alpha plus beta is 90 degrees, because the sum of all three is going to be 180. But the next thing I want to do is prove the Pythagorean theorem, which will put a few of these concepts to use, okay? So we got the right triangle, sum of these two angles, 90 degrees. Of course, the area is 1/2 a times b. We would also know that. So the next thing we're going to do is prove the Pythagorean theorem. Okay. So next, Pythagoras. And the construction, right, we're referring to this triangle, and we know from the sides, a squared plus b squared equals c squared. But we want to prove it. Proof is always fun. Yeah, let's go ahead and do it. So here's a construction. The construction to prove the Pythagorean theorem, you get it all on this board, is to draw a large square. And by the way, in your notes, be generous, because everything we're doing is good practice, okay? So draw them big, don't put a little tiny square in a corner somewhere. Make a big one. So there's a square, and what we're going to do is divide the bottom into A and B, okay? And I'm just making this up, but this should work. So now I take B here, that length, I've got A and B again. I take this same length over here. I've got A and B, and then all the way over here as well. So same length, A and B. And now what I'm going to do is connect these points that I made here. I'm doing this all freehand. And the next question for you guys is what I just drew also a square? And can we prove it? You know, we started with 90-degree angles. Okay. So these are by construction 90-degree angles. And we can label those angles again. This is kind of a sub part of the calculation. So if I call this alpha and this beta over here, then I can just by construction see that I've got an alpha here as well, and therefore alpha plus beta is 90, and I can repeat that all the way around. So yes, what I have inside the big square is a smaller square. So area of the outside square, okay, is going to be equal to A plus B, the quantity squared. Okay. Now let's go ahead and just name these other ones C here. Area of the inside square is equal to C squared. Let's see what we have here. A sub outside is equal to A plus B, the quantity squared. If you expand that out, you get A squared plus 2AB plus B squared. Okay. And actually the proof is almost staring us in the face. So that's the area of the outside square equals a squared plus b squared plus, now this 2ab is 4 times 1/2 ab. But 1/2 ab, okay, ab, I'll shade one of these in red, okay. We have 4 of these. Okay, we have 4 of these, 1/2 ab. So a squared plus b squared plus 4 of these is our outside square, and that means that this is a inside is equal to c squared. Okay, so we got c squared, a squared plus b squared is c squared, because we've got that c squared plus 4 of these outside ones. Okay, so that's a lot of fun. And we've demonstrated the theorem of Pythagoras now. Something that gets used quite a bit. So yeah, once it's been done, you want to go back to the empty square and do the construction yourself. Make sure you can draw this conclusion here, and then you will have, you'll understand something. So yeah, those of you who don't have that much practice with these, just take it as a fun exercise. Do the sketches, do the drawing, think this through, like this expansion here, 2ab plus b squared. You want to make sure you saw, and you'll be getting useful practice with algebra. Okay, I'm going to check the clock, see how we're doing here. Okay, excellent. We can do a little more. So we have the Pythagorean theorem, and this next exercise is going to have to do with the area of a circle. Okay, good. So, area of a circle. And I'll have to start with the definition of a circle. And I should have actually brought a string. Hold on a moment, I may have something here. I can actually take a loop of string and draw a perfect circle. But, so this is more to remind you that it's possible, because I don't have the loop string right here. But yeah, you take, for example, you have a piece of cardboard, you want to draw a perfect circle. You take a tack, loop a string, a pencil, loop a string, draw your perfect circle. Okay. So, the circle. So you've got the center of the circle, and like I said, you've got that construction, so you draw your perfect circle. There's the center, and that loop of string that you used to do it for your construction, that has the length of the radius r. Okay. So a circle is all these points equidistant from this point, the center of the circle, and that is the radius r. The circle, radius r. Now the question is, what is the area bounded by this circle? And you may know it, but can we prove it? Okay. Well, first of all, we need to introduce the circumference of the circle and the number pi. Okay, so we want the area So first, pi is equal to the circumference. Say if you were to lay a string on this circumference here and measure its length, divided by the diameter. So this is a number, you can look it up. And we'll go ahead and call that circumference C. And the diameter we know is twice this radius. So for the diameter, we'll write 2 times r. So this defines pi equals C over 2r. And there are different ways of obtaining it. That's a mathematical task, really. You could draw circles and measure really carefully, but the first several digits are 3.14159, keeps going on and on and on, okay? So that's how many diameters there are in a circle if you lay them around there. Okay, so that's the first point. The next point is, again, what is the area? Next, the area in there. Now this construction goes back to classical antiquity, but it's very interesting and a little bit sophisticated. So what we're going to do is another nice circle here. You have a radius r, and we're going to do an estimate by putting this circle inside a box. So it fits perfectly in this box, which means that the area of the circle is less than the area of that square. Okay. So area of circle is clearly less than the area of the square, and the area of the square is exactly 2r, the quantity squared, which when you multiply that out, that's 4r squared. Okay. So that's an estimate. But can we do better? The way we're going to do better, I've got another color here, is we're going to make a bunch of triangles like this, so that we'll draw tangents to the circle, and these will all be triangles. In fact, we're going to fill in the entire strips. They go outside. Okay, these straight lines are on the outside. I'll do one more. Okay, it's not so perfect, but you get the idea. In fact, let me get this one. Point is this: if I go around the entire circle like this, the area of the sum of all these triangles will be slightly larger than the area of the circle, because I have all these little extra spaces here that I'll kind of indicate with blue. I've got these little extra areas all the way around, but the area of the sum of the triangles is approximately and slightly greater. So let's call this one here area of the sum of triangles is equal to, and now this Greek letter sigma, one of the ones you guys printed out, that means sum of, summation. So that means all of, it's the summation of all of these triangles, and all of these triangles are interesting. They're essentially the same, and they are 1/2 base times height. Okay, so it's the sum of a bunch of 1/2 base times height. 1/2 base times height. But the height of these happens to be exactly the radius. So it's 1/2 the base times the radius of our circle. So what I can do is pull the 1/2 out front and the r. And now I'm just left with the sum of all the bases, which are my red lines here. So the base of my triangles are on the outside of the perimeter there. And these here add up to approximately 2 pi radius, because that's the circumference of the circle. So what we're getting here is approximately 1/2 r times 2 pi r. Area of the sum of the triangles. Notice I've got that approximation here, and now the final stage of the calculation is to imagine I draw many, many very tiny triangles, narrow ones, so that these little errors keep getting smaller and smaller. In the limit of infinite many small triangles, this polygon turns into a circle, and I get the exact thing. So right here, I have to do what's called take the limit, and when I do take the limit, I'll end up with 2's canceling pi r squared. So in the limit of infinity triangles, we get area bounded by the circle is equal to pi radius squared. That's actually, like I said, that's a sophisticated little process. And if you guys had calculus, you may have run into this kind of thing, the idea of taking a limit. But you don't need calculus to have the idea of taking a limit. It's all actually up in this picture and what I've discussed. Okay, once more I'm going to check the time. I think we've got enough here for today. Okay, that's perfect. Okay, so let me just leave you with this idea. The constructions I did today, you put them in your notes and practice them from scratch, and just, practice all of these moves here because they'll become easier to you. And one thing we are going to reason with a lot through the semester is these kind of basic formulas. Here I actually just showed you how it's derived, because that's good practice as well. But the type of algebra we'll do during the semester is this type of algebra. For example, I use circumference as 2 pi r. That's a cross multiplication here. Circumference is 2 pi r. Let me actually put that as a note. Yeah, I'll just use this part of the board to wrap things up. Note on algebra. This is one thing we will do very, very often. So if I have pi as a definition of circumference over 2 times r, then I multiply both sides by 2r. 2r, and then of course on the right side 2r cancels, and I'm left with c equals 2 pi r. Okay, so again, this is the kind of thing we also want to practice, and that's something I used in this last step right here. Okay, good. Do that, and we'll see you next time.